Hello, everyone. Welcome to Tectonics. The lecture today is going to be a case study. We're going to look at Taiwan. Taiwan is an island in the Pacific off the Asian coast. It's a very tectonically active area, and it's an area that we find particularly interesting because it is one of the few examples we have today of active arc-continent collision. And in fact, this is really an example of almost collisional tectonics that are ongoing today. So processes that we often refer to sort of generically as mountain building are observable occurring today. That is, they're really active and we can see the processes today. That includes things like the geomorphic processes. These are occurring at relatively high rates because of the high tectonic rates, but also because this is a region where there's quite an important climate influence. And that climate influence is really manifested through typhoons. It's on the edge of the Western Pacific, and in this area, it's in the typhoon belt, and so it gets a lot of these large tropical storms. And this will produce this interaction then between the tectonic processes, the geomorphic processes, the mountain building, and the climate-driven erosional processes. So for us here in Switzerland, there are also some interesting similarities. I put together just a few slides for another purpose once when I was at a meeting in Taiwan. So I share them with you. They're not very scientific, but it's a little bit fun. It gives us some of the similarities in both the geography and the geology between Switzerland and Taiwan, which are actually surprisingly similar. So these are two maps, for example, of Switzerland and Taiwan at the same scale. You can see the scale is actually not that different. There are other things that are roughly the same. The size is, as mentioned, that's pretty close to the same, broken up into 26 cantons, 19 counties. The high point in Switzerland is 4,600 meters, a little bit lower in Taiwan. It's just under 4,000 meters. GDP of the two countries is actually remarkably similar. One of the biggest differences, in fact, the population, where Switzerland's 8.5 million is then matched by Taiwan, which has 24 million. So it's a little bit more crowded there, a little smaller, and quite a few more people. The geology is also remarkably similar. Switzerland is dominated by the Alps, which is a metamorphic orogenic belt that you see sweeping through here in blues, oranges, and purples. With a foreland basin really on both sides, mostly on the Italian side in the south, but then the morass basin up in the north. Taiwan is also an orogenic belt. This is a metamorphic belt in greens, blues, and purples through here, for example. The thrust belt along this side. And out here in the coastal plain area is again a foreland basin. This is sediments, young sediments that are being deposited here. So we have this, again, this mix of foreland and orogenic belt. And also similar is the fact that most of the people tend to want to live in the foreland for some reason. It might have something to do with the lack of mountains. But the population density of the two is dominated with this high values out here in the coastal plain, high values out in the foreland of the Alps, relatively low concentrations in the mountainous areas. There are even little similarities, like little hotspots of population in valleys such as the Ticino or the Valais region, where you get a little bit of flat land, makes it a little more habitable for living. Because both countries are mountainous, they tend to be rather susceptible to natural hazards, things like floods. We could also talk about landslides and other features of high relief geomorphic terrains. Taiwan has a lot more active earthquakes, but given it's the young age and the active tectonics, but both areas are susceptible also to earthquakes. Famous mountains, maybe not so famous in Switzerland, the mountains of Taiwan. This is the Yushan, the highest mountain in Taiwan, which is least famous in Taiwan, if not around the world. What's maybe more famous is actually this not mountain, but very high structure. This is the Taipei 101 building, which is a 500-meter high skyscraper built in Taipei, which was the tallest building in the world for about 10 years. Now it's been superseded by a couple of other buildings, but again, very well-known characteristic of Taiwan. Lots of mountains means nice trails. Spectacular scenery. It's a fun place to work in Taiwan because of these fantastic mountains and high relief. They tend to be a little less safety conscious, maybe. Notice no handrail here compared to the Swiss counterpart, but still a good trail. Wild animals of the areas, okay, not so wild perhaps, but they can be hazardous in both cases. Run into water buffalo in Taiwan occasionally. Swiss cows are not super aggressive, but I've been surprised on occasion. A few differences: better skiing in Switzerland, nicer beaches in Taiwan. Every area's got its own climate and characteristics. But really, what's is important for us as geologists is that these are two of the classic natural laboratories of the world. Both of these areas have a very important history in tectonic geological studies. The Alps, of course, being one of the first places to be studied for continental collision and orogenesis. But Taiwan has been also a very popular area over the last 30, 40 years anyway, because this is an area that is undergoing active deformation, active collision today. So to come back to more of the scientific side, where is Taiwan? What is it in response to? What is its tectonic setting? This is the Western Pacific. We're looking at this area, if you look at the inset first, between the Eurasian plate, the Pacific plate, and the Philippine Sea plate. Taiwan is sitting right here in this corner, which is expanded here. So here again is the Philippine Sea plate outlined more or less here, with Taiwan sitting right here in the corner between Eurasia and the Philippine Sea plate, but where the plate boundary makes a turn here. And I'll certainly talk about that more in a minute. The Philippine Sea plate is a little special in the sense that it is an oceanic plate. It's only oceanic lithosphere, but there are no active ridges on the Philippine Sea plate. That means that it's a relatively old plate. It's not growing at the moment at any point. And without ridges, that means it has no modern magnetic anomalies to establish its motion. So it's actually quite a difficult plate to determine its direction of motion, or its history for that matter. We have estimates from various other ways, but that does not include magnetic anomalies because there are no ridges. It's surrounded completely by subduction zones. So that means that it is being consumed. It will eventually disappear. This is a plate that will be gone in some millions of years. But the subduction is not simple. In fact, it's in some cases, the Philippine Sea plate is the upper plate. So for example, here in Izumonin and Marianas, this is the Pacific plate is here subducting underneath the Philippine Sea, whereas in the Ryukyu Trench, the Philippine Sea plate is going down underneath the Asian plate. So in some places it's stable, in other places it's disappearing. Taiwan is a little bit special in that it sits right at the transition between two trenches. So here, the Manila Trench, which is actually consuming the South China Sea, this oceanic plate or this oceanic lithosphere here, is subducting underneath Luzon. That's along this this trench here, along Luzon to Taiwan. But to the east then of Taiwan is the Ryukyu Trench, where the Philippine Sea plate is going down underneath the Ryukyu arc here. So we have two polarities of subduction, where Philippine Sea plate is both the downgoing plate and the upper plate, and the two are coming together somehow right here in Taiwan. So if we zoom in on that area, here's Taiwan now, two maps here on the upper left. Here's sort of the sketch. You can see the island here. This is then the Ryukyu Trench out here. So this region in here is where the Philippine Sea plate is subducting underneath Asia. And over here is the Manila Trench, then where the South China Sea is subducting underneath the Luzon Arc. The Luzon Arc is shown in pink here, is coming up here. So this is the trench. This is the active arc in here. This is then moving towards the northwest. This is the velocity here of the Philippine Sea plate with respect to Asia. So at about 80 millimeters per year in the northwest direction, like this. That's bringing then the Philippine Sea plate towards the northwest, where it goes down into the Ryukyu Trench. But over here, it's bringing it out over the top of the Asian plate, subducting the South China Sea. As we move to the north out of the South China Sea, this is a passive margin. And we're moving up then onto the Chinese passive margin. That is, this is the Asian margin along here. So this is continental crust, continental lithosphere up here. Because this is the downgoing plate, we have a slight problem here in that this continental crust is moving into the subduction zone where it doesn't want to subduct because of its buoyancy. And therefore we have this collision zone then between the Luzon arc here and the passive margin here. So to the south, happy subduction, oceanic lithosphere, it's going down underneath the arc. To the north, the arc is colliding then with this passive margin. And Taiwan, the island, is this collision zone. So the north-directed subduction in the Ryukyu Trench actually doesn't play a very important role to what we see in the geology here. It does to the far north. I'll show some examples of this, but mostly this zone in here is dominated by this collision then between the Luzon arc rocks here and the continental margin here. We can see this active ongoing collision or convergence in the GPS. This is the geodetic velocity of the of a number of stations on the island. What you can see down here, for example, start down here. This is an arrow going to the northwest that's sitting on one of the islands out here that's part of the Luzon arc. So that's this bit here. This then is giving us pretty much the true plate velocity then between the Philippine Sea Plate and Asia up here. And again, here's this northwest vector. As we come onto the island, then what we find is that these arrows are all a little bit shorter. What does that mean? I could actually get a little bit longer here, which is kind of funny, but they're starting to curve off to the left, but they're getting progressively shorter until we arrive up in here, say this red zone, which is again the Foreland Basin. Now we're onto Asia proper in a sense, because we see in fact that these arrows are going to zero. That's no relative velocity. Again, this is the relative velocity of Philippine Sea Plate to Asia. So if it's zero, that means this is in fact Asia, right? And none of this is actually moving at all with respect to Asia. This is moving towards Asia. This is convergence, right? So this area must be contracting and deforming because of this difference in the velocity. So we go into the far north up here, we see that everything either goes to zero or has some very funny directions in here, for example. This then is where we are being influenced by subduction of the Ryukyu system into the Ryukyu arc system. And again, I'll zoom in and show you this, but what you can really see is that there is actually very little convergence, at least on land here. The convergence must be taken up along the Ryukyu Trench down here, and this area is largely undeformed. So let's look at the structure of these subduction zones. So this is looking at a kind of oblique view of the subsurface underneath Taiwan. So we've sort of removed the Philippine Sea Plate. We're looking to the northwest. So this is south, this is north. There's a north arrow down here. And what we're looking at here is earthquakes in the Benioff zone of the Manila Trench system. So this is then the Asian slab going underneath Philippine Sea Plate, and we're looking at depth contours along that reconstructed slab. So what you can see is this dipping down to the east of South China Sea lithosphere and parts of, in fact, the continental margin. The margin boundary must come through here somewhere. But we can see that there is, in fact, a slab system going, at least in this interpretation, really almost all the way to North Taiwan. Certainly into central Taiwan, we still see this Asian slab here. And the whole system then is somehow diving into the Ryukyu Trench here on the other side. And in fact, we can do the same and try to have a look at the structure of the Ryukyu Trench, or the slab of the Philippine Sea Plate. So this now is looking again, here's Taiwan south to north. So north is now to the left in this figure. This is the Ryukyu Trench coming around here, going up to Japan up here. Philippine Sea Plate, you can see by these contours and again by the earthquakes. These are the earthquake depths along the Benioff zone here again. We can see this dipping slab coming down into the deep mantle underneath the Ryukyu arc. So again, over here, we were looking at the slab dipping into the picture down to the west, and that is somehow fighting for space with this slab here that's dipping to the north and northwest along the Ryukyu system. And this is, again, maybe 1/3 of northern Taiwan is really sitting above the Ryukyu slab. The rest is dominated by the subduction of the Manila Trench. So in sort of a block diagram form, here's the sort of the picture then that must be happening somehow. It's very cleverly hidden the most complicated part of the system where these two slabs must somehow interact. But again, here's the island of Taiwan, Eurasian plate coming down to the south. So south of Taiwan is a perfectly happy, normal sort of oceanic subduction system out here. To the east of Taiwan is, again, happy oceanic subduction of the Philippine Sea Plate underneath Eurasian plate in the Ryukyu Trench. And where things are messy is where we get up into this corner here where the slabs can't be going both down and staying up. So there must be some kind of complicated deformation going on in that corner. In fact, there is a bit of a space problem in that with this, say, looking down here in the lower left, with this slab going down here and this slab going down here, the two are going to have to somehow compete for space here. And really, we have an unstable tectonic situation where this, in fact, one of these slabs probably has to tear or somehow deform strongly in some way in order to allow space for this. And one of the easiest ways to do this, a way that kind of makes some sense anyway, is that the Asian slab could be tearing off laterally here, sort of from north to south, as the Philippine Sea Plate slides into this corner and is subducting down underneath the Ryukyu arc over here. So if you can visualize that, the slab of the Philippine Sea Plate slips into the corner here, and as it moves to the northwest, it sort of tears off this slab of Asian material in order to fill in that gap. But somehow there's definitely this sort of space problem, and the fact that you can't have a slab going both up and down, or part of the plate being subducted and being the upper plate without tearing that plate somewhere. So the collision zone itself to the south, again, if we look to the south of Taiwan, it's happy subduction of oceanic lithosphere, but we can see that this arc is coming into the island here, and the south, the passive margin of Asia that goes down into the South China Sea is coming in sort of in this direction, and the two are rather oblique to each other. So again, if we think about the motion in this direction, northwest motion is relative plate motion, you can see that that's bringing this arc into collision with the passive margin. And furthermore, that has to happen first in the north. Okay, so if this was truly a linear structure, the collision is already quite old up here. This collision must have happened some probably millions of years ago, but this collision zone is now actually propagating to the south. So you sort of think of the relative motions here as kind of like the closing of a zipper, that this is here it's closed and it's slowly closing down to the south. So we're seeing really just the initial collision down in the southern part of Taiwan, whereas it must be much older to the north. And as we go forward in time, the entire South China Sea basin is going to close, where Taiwan is like the zipper that's running down through your jacket here, closing up this basin, bringing the Luzon arc and the passive margin together. So if we think about that in terms of time, and we can reconstruct this, we can think about the old, if we go back like 6 million years ago, this would have been the Asian margin along here. The Luzon arc, if it were straight, would come up to a projected point, something like this. And this is where that initial collision would have occurred between the Luzon arc and Asia. With time, if we bump down, say to 4 million years, this collision point, these are going to come together. Again, this is the closing of the zipper, and that onset point of the collision is going to move south 2 million years to the modern. It's propagating down to the south. And this is quite interesting from a geological point of view, because that means that by looking at the geology in North Taiwan, what we're seeing is something like a 5 or 6 million year old collision. We move down to the southern tip down in this area, it's really zero. This is where the collision is just initiating. In fact, we know that. We go down here, it looks like oceanic subduction. So we have this, so we sometimes refer to as a space-time equivalence. By moving north in space, we're going back in time, looking at the equivalent processes or that would have happened at an earlier time. And that's another reason why Taiwan's a nice place to study this process, because we can see what things looked like before collision, during collision, and even after collision. So it's also why when I mentioned that the Ryukyu arc is probably less important than the Manila trench system, the Luzon arc system, because most of this geology is in fact recording this older collision that happened between Luzon and Asia, and the Asian margin up in here. And the geology of the island, in fact, from north to south is quite similar, other than this sort of time of orogeny difference. But we don't have a very strong effect from the Ryukyu system. We're really seeing what this early stages of the collision between the Luzon and Asia. So let's look at some of the geology, look at a couple of geological sections across here. So here again is our block diagram view. If we are to look at the, say, some profiles across here from A, B, C, D, we're moving south to north from the oceanic subduction up into the collision zone. Some of these sections are shown over here on the right. So in particular, starting with the section at A, this is south of the island of Taiwan. So this is pretty much all underwater except for parts of the Luzon arc, but this is your typical sort of oceanic subduction system. We have an arc, we have a accretionary wedge out in the front that's being formed by the subduction and off scraping of materials here. We have a forearc basin between the two. Go back a few lectures and we'll see pictures that look very similar to this sort of thing. The passive margin of the continent is still somewhat removed, depends on exactly where we go across this section, right? In this particular case, you can see that there are some thrusts from the accretionary wedge that are propagating out. In fact, you can't see exactly where the section is, but they're coming out into this region. Maybe that's a thrust in here, maybe even here, but gotta be careful we don't mix normal faults with the thrust faults that are associated with the accretionary wedge out here. But the collision in any case has not really started, has not really occurred. If we move up north a little bit to this section B, now we're crossing the southern tip of the island. At this point, there's no oceanic crust exposed anywhere out here. So we're really getting into the first stages of the collision. And what we see in this section here, so this is the B section now. So here's the Chinese passive margin, and that's now moved into the collision zone, in that now the accretionary wedge is starting to cut off slices of that passive margin. It's starting to accrete relatively thick sedimentary units, or possibly even parts of the basin. The accretionary wedge is growing. The arc back here in the back is actually extinct now. So the volcanism actually gets cut off about here, right, where we start to lose this oceanic subduction, which is interesting, right? So this is the rocks in here, which are exactly the same as the rest of the Luzon arc, but there are no active volcanics in this area. So the arc has become extinct. We have what's here now called a forearc domain. The forearc basin is gone, right, which is interesting. It's either been thrust and shortened and sort of accreted into this part of the thrust belt. This would be, by the way, the retro thrust belt in this system. Then we've got a pro wedge out here and a retro wedge thrust system back here. The forearc basin is either part of this thrust belt now, or it's been subducted. And there are arguments, you can see at least in this interpretation, that part of the forearc crust is actually slid underneath the arc. So this is the piece that would have been up here, and now it's sort of slid underneath the arc as we've shortened this area. But somehow the accretionary wedge and the arc are now almost right next to each other, right? So this distance is shortened a lot. So there's a lot of shortening between here and here. And one way of doing that easily is just to slide a block out of the way here, right? So the accretionary wedge is growing, the forearc has disappeared, the arc has gone extinct. That's sort of the picture. If we move north, one more, this is section C. This is really right across the middle of the belt now. At this point, the passive margin has subducted underneath the accretionary wedge system. And the whole, well, started to now scrape off pieces of the basement and accrete those into this orogenic wedge. So the wedge is getting much, much larger. And it's not only including sediments from the downgoing plate, but also slices of basement from this plate. It's building then quite a large accretionary wedge system that's again back thrusting. The arc is now almost covered by these back thrusting systems in here. And we go one more section way to the north, but still in the collision zone, or right at the edge of the active collision zone. We see really kind of the mature stage of this, not so different from C, but you see again a large accretionary wedge, passive margin under thrust underneath, arc is almost invisible. There's arc rocks left, forearc rocks left, but much of this area is now exposing deeper metamorphic rocks that were accreted down deep in the accretionary system. Right, so here you can really see what I was talking about with the space-time equivalence, that this is, here we're looking at 4 different sections in space, but in fact you can get to this one from this one, in the sense that this is a time sequence as well as a space sequence, early collision, late collision. Just to be complete, let's move around the corner and look at one more section, which is through the Ryukyu system here. So this is section E, and that's shown over here then. This is south, this is north, so we're looking up here onto stable Eurasia here with the Philippine Sea Plate, then subducting underneath Ryukyu, right, at the Ryukyu Trench. Here now it's starting to look again like what we would refer to as normal oceanic subduction, but now the upper plate is continental. And we have, again, an accretionary wedge out here. We have the active arc up here. And interestingly, we have here an extensional basin. So this would be a back arc basin. So here we have a continental upper plate system, but it is undergoing extension. And we're forming what's called the Okinawa Trough. That's this back here. You can see it in the section here, but this is a back arc basin that associated with this subduction. So in this case, that implies that this arc is moving towards the trench in response to this opening in the Okinawa Trough, and that's relative then to stable Asia. So we're having an active extension in this region that probably includes northernmost Taiwan. So if we look at this northern Taiwan, just to look at again at the influence of this Ryukyu Trench system, what we have then is this subduction. We have the active arc. We have this back arc basin in the Okinawa Trough. So this is undergoing extension. That extension is coming probably on land into this, at least into northernmost Taiwan, this region right here. So in fact, the mountain belt here is actually broken up. And we have this little triangular zone in here, which is very close to sea level. This is the on-land continuation of the Okinawa Trough. So presumably this was all mountain belt until very recently. And now as this Okinawa Trough propagates on land, it's starting to tear the mountain belt in half. And this central graben area is now dropping down to very close to sea level. So sort of the kinematics of how this must work, this is sort of a cartoon version of this region in here. We have a back arc basin region. We have the trench here. That back arc extension increases to the right, to the east here. So it's less at the tip and increasing in this direction. And that results in kind of a rotation of the trench system, right? So there's been more extension. This trench system has to rotate down over here more than it does here. So we end up with a motion something like that. That point is somewhere in here on Taiwan, which is why we then end up with a little bit of extension on land. And if you remember, if you go back and look at the GPS field, there were all these very funny velocities in here. That's because part of this is actually dominated by the rotation. Most of the convergence has stopped in this region. And what we really have then is extension, some rotation. Velocities in here are actually moving to the southeast. And stuff here is responding maybe with a little bit of northward motion, but it's almost attached to Asia here, and really things are dominated by these normal faults in here. All right. Well, Taiwan has also been very famous for its role in critical wedge mechanics. This is work that has been done in the Western Foothills region, it's called, which is really the frontal thrust system of the pro wedge, where it's coming out into the Foreland Basin. And work, for example, like this section back in the 1980s was reconstructing the deformation of the thrust belt. So this is the reconstruction below of this cross section right here, where these thrusts are all pulled back to show what things looked like prior to this convergence. It's quite a bit of convergence along this section. But this is the kind of picture that was drawn and interpreted in terms of critical wedge mechanics for this fold and thrust belt. And if you go back to the original papers on fold and thrust belt, you see there's the important convergent belts of the world at this time, Himalaya and Taiwan. Taiwan is relatively prominent. This is the famous alpha beta sort of plot to look at the sorts of taper angles that were found in Taiwan. And when you do these sorts of reconstructions, you end up with these big gaps, right? You appreciate where this is coming from. There's big holes in the ground here. This is not paleotopography. This is material that's been removed by erosion, right? So as this thrust belt was forming, yes, it built this big critical wedge, but the front of the thrust belts or the thrust sheets were all eroded off, and that's what leaves these sort of gaps and holes in the interpretation. At sort of a larger scale, we can then see the what's involved in the thrust belt here, and we can also see that there are internal kinematics that are relatively complicated compared to things like the simple sandbox models that we're showing. In particular, early stages might be dominated by oceanic sediment accretion into this accretionary prism or deformed forearc. But with increasing convergence in time, more and more of the deeper material tends to be brought back underneath the orogenic wedge, where it can then be deformed, scraped off of the downgoing plate once that becomes continental, and attached into the base of the orogenic wedge. And this is this process of basal accretion or underplating, where these slices of material are added. This here, for example, is a sort of antiformal structure, or a knapsack, if you'd like to call it the alpine terms, or a duplex structure in structural terms, where we see the sequence of thrusts 1, 2, 3 as material is added onto the base of this antiformal stack of thrusts. This means also that the material is coming from relatively deep in the crust. If it's then being eroded off the top and accreted onto the bottom, we end up bringing up relatively high-grade metamorphic rocks from deep in the crust. I say relative because it's not really high-grade. We're not bringing up lower crustal rocks, but it's rocks that were buried underneath this accretionary wedge to a substantial depth. So here's sort of a simulation of that sort of process in a sandbox, which are, like, again, useful analog models to show how this happens. In this case, they're looking at what they're calling a proto wedge, where there's some sort of an accretionary wedge developed, but then a stratified material that's brought underneath this and progressively deformed. So it's forming both this frontal thrust belt out here, whole series of thrust sheets out here, but there's also material then that's getting pulled back into the system, and it's being accreted then onto in this set of deep underplated naps underneath this this older what's really probably a stable accretionary wedge. And then with time, then this sort of a process leads to this sort of structure where we do have this frontal pro wedge of relatively shallowly thrusted sediments and, you know, superficial rocks anyway, and then a region of deep underplating where this material is added on deeply. If it's then exhumed through erosional processes on the top, then all of this stuff comes in, it gets stacked up, and it's brought up to the surface, and we end up seeing sort of what's really sort of the deeper levels of this orogenic system. Right, so this process can be even more complicated if we start to recognize there are things like shear, like origin parallel shear across the mountain belt. So this is here's a cross section again of the Taiwan wedge. Here's the accretionary wedge system. This, what's being referred to as rigid buttress, is really the old arc, the Philippine Sea Plate, the parts that are relatively stable. And it's actually moving a little bit to the north with respect to the main orogenic belt, which leads to this central region of shear. So exactly in this area where I was just arguing for underplating and metamorphic rocks coming up to the surface, we also have this ductile deformation that results in both shear, both pure shear or simple shear in this direction, but also sort of a stretching shear in the middle of this zone. So this zone in the center ends up being both highly exhumed, metamorphosed, and also deformed. And much of that deformation is ductile because we are bringing stuff up from at least mid-crustal levels. So the sequence of thrusts and the structure of the wedge is also influenced by what is being accreted. And this is actually not dissimilar from what you've probably seen in the Alps, where the argument is that the orogenic belt is actually formed by the old passive margin, in that case of Europe. Here we're looking at Asia, but again, we're looking at a pre-collisional geometry that's dominated by these normal faults, by the stretching of the passive margin, and then by the thick sediments that are deposited over that margin. So the sequence looks something like this again: basement that's been thinned progressively towards the oceanic crust, and then we'll have shelf and slope sediments going into a deeper water-facing sediment here, and these will then all be progressively accreted into the wedge as we build an accretionary system here. So as the collision propagates in through the continental material, we'll see this progressive accretion of deep water and then shallow water sediments that are being scraped off of the plate here. So again, another section to show how this appears also in the geologic map on the left. So the current deformation front of the system is running somehow through this region. So this is the foreland out here. These are the thrusts of the pro wedge, the accretionary complex out here. To the south, this is the deformation front. It comes on land, it kind of swings around like this a little bit. But the important point is that here we have exhumation and exposure of what are really the sediments of either the foreland basin that's now been incorporated into the thrust belt, and that's things like these units in here, going from the yellow, which are modern Pleistocene, Pliocene, mostly Pleistocene, I guess sediments are in yellow here, into what's called the Western foothills, which is the fold and thrust belt here, which is going then from Pleistocene to maybe the upper Miocene in age. And this is going down these are all clastic sedimentary units, but going down into progressively deeper water as we go down into the blues. So that's kind of this region in here. When we get into the higher mountains up in here, for example, this area and back in here, then this is what's called the Shushan Range and the Central Range. These are now the either slates that are mildly metamorphosed sedimentary rocks, or the deeper metamorphic rocks that have been underthrust down into the forearc system here. And these are then going back to as old as the Eocene in age here. Right, and then finally in the back we have the volcanics, if you'd like, it's not really indicated very well here, but this is the volcanics of the Luzon Arc that's coming up through here, which is then sort of the backstop of the whole system. So progressively deeper exhumation. We see this also over here, where we're seeing in the foothill belt, then the cover rocks in the Shushan Range, then that we're getting down into the deeper. These are metamorphosed at least slightly into slates and schists so again, still mostly sedimentary protoliths, but a deeper exhumation into the orogenic belt. And you've seen this sort of diagram for the Alps, but this is again showing that same sort of idea that we're looking at a progressive sedimentary sequence from deep water, particularly deep water here, to shallower water sediments that are then overthrust one on top of the other. So this is going down into the Mesozoic basement, for example. This is overthrust then on top of the deep water sedimentary units. This would be the Miocene continental margin, carbonates and clastics from the continental margin. And these are overthrust on top of the Pliocene Pleistocene, which are mostly foreland basin deposits that were deposited somewhere between the Asian coastline and Taiwan here. Along with the internal deformation, there are other characteristics that indicate the kinematics of the internal wedge. So, for example, the foliation in the rocks can also reflect the multiple stages of deformation. So I think everyone appreciates that you get a foliation in ductily deformed rocks that's typically perpendicular to the shortening direction. So for example, you'll get an axial parallel foliation when you have folding due to compression. What's interesting in Taiwan is where we can actually see the doubly vergent nature of the wedge deformation in the foliation, in that in the pro wedge on this side of the system, where material is coming in directly, there is compression in this direction, and there's a foliation developed in the ductile rocks that's oriented something like this. But in the retro wedge, these same rocks are then carried into the retro wedge and deformed again with a new stress orientation, and that can fold the original foliation. So we end up with a double foliation, or a crenulation cleavage, as it's sometimes called then, where we see both of these phases of deformation. And we can see that, for example, these are the foliation directions on each across the traverse of the mountain range. On the west, in the pro wedge, there's one cleavage, one phase of deformation. And then on the other side of the system, the east or the retro wedge, we see a double phase. We see a second phase of folding and cleavage and cleavage development, something like this. So I'm going to go back and review quickly 2 slides or something thermochronometry, because this is an example where we're next going to use thermochronometry to say something or to learn something about the kinematics and the rates of deformation and the rates of exhumation in the mountain belt. So this is your quick review. Remember that thermochronology is measuring the timing at which, or the rates at which rocks are approaching the surface of the earth. That is, they're really giving us the time that it takes to come from a high temperature, where no daughter product is retained, up to the surface. Right? So we're going to now use this tool to try to assess something about both the paths and the rate of motion from some depth deep in the earth up to the surface of the earth. So what depth? Well, this depends on the thermochronometer. There are a number of different thermochronometers that we can use then, and this is, again, a review. We saw this in an earlier lecture as to what that closure temperature is for different systems. We have, for example, the apatite systems, and this depends on the cooling rate, right? So this is the effective closure temperature as a function of cooling rate. The dependence on cooling rate is a little weak. This is 4 orders of magnitude, so it's not as important as the temperature. But again, these are the systems we look at: apatite, uranium, thorium, helium dating, apatite fission track dating, zircon, uranium, thorium, helium dating, zircon fission track. There are a couple of odd ones in here that we won't really worry about: titanite, helium, argon, and feldspar, and then higher temperature systems. So here's an example of a data set, thermochronometric data set that we want to now try to interpret. These are zircon fission track gauges from basement, that is from outcrop samples, distributed across a number of transects across Taiwan. So zircon fission track, if I step back for a second, that's down here. At the rates we're looking at, something like this, it's around 200 degrees C, probably a little bit less, but somewhere in the order of about 200 degrees C is the closure temperature. So these are the ages in millions of years, or telling us the time that those rocks then took to get from 200 degrees C up to the surface. And we're seeing numbers as low as under 1 million years. We look over here, for example, here's 1 million years, 1.6, 1.9, 2.9. So it's taking from 1 to 3 million years right here to come up from a depth of about 200 degrees C. What kind of a depth is that? Well, it's probably a high geothermal gradient here, something like 30 to even 50 degrees C per kilometer. If it goes as high as 50, 200 degrees would be about 4 kilometers. So we're eroding off or bringing material up from a depth of about 4 kilometers in 1 to 3 million years. What's interesting about these ages, though, is that there are sort of 2 sets of ages. In fact, this is showing some blue dots that there are no ages shown. Those blue dots are actually areas that have zircon fission track ages older than 7 million years. Whereas the, this key is actually backwards. This is backwards. Flip these 2. The red ones are places where the zircon fission track age is younger than 7 million years. All right, so this shows that there's a large region with young ages, and it's sort of surrounded by a larger region of older ages. Why is that important? Well, remember that the orogeny here started about 5 or 6 million years ago. So those blue dots, the older ages, are showing us times or ages or rocks that have not gone down to great depth and come back to the surface during this most recent orogeny. The red dots, on the other hand, are the regions where we're seeing exposure of the deep crust over this relatively short time span. There are other ages that are showing a sort of a similar pattern. This is zircon helium ages. These are also showing there's some very young ages. So the zircon helium closure temperature is just a little bit less than the zircon fission track closure temperature. Again, we're seeing ages under 2 million years, but 2 to 5, 5 to 7, and so on. And again, these are showing a pattern where the youngest are sort of here in the center of the mountain belt. There's a little zone of older ages in the middle, then they get young, and then they get older again out here. But the pattern, the general pattern, especially, I'm going to go back to the zircon fission track ages again. I'll go back and even show you the ages again, just to remind you, these are the young ones. These are all older in blue here. But the pattern is really one where they're younger in the middle and older out here in the front, right? So, and the reason for this is the kinematics of the deformation within this orogenic wedge. The young ages are coming from these zones back in here and sort of the middle of the mountain belt, where the kinematics of the paths that the rocks have taken are relatively deep into the crust. So again, these black lines here represent paths that a rock would take as it's accreted into the front of the orogenic wedge. It's buried deeply under the wedge. Maybe it's even accreted in a thrust sheet that gets carried under the wedge and attached to the base. And then it comes up to the surface in a almost vertical path here, or a steeper path here, shallower out towards the front. So a rock that's sitting back here, say in the back retro wedge of the system, has come straight up from relatively deep depths, high temperatures, like these higher closure isotherms. Rocks out here in the front, not so much so. They've been accreted into the front of the pro wedge, for example, and then they've been just very quickly brought back up to the surface again. That means they've not gone down to temperatures high enough to be reset by this sort of tectonic burial. And this then is why we see all these younger ages, in fact, exposed back here, and older ages out in the front of the wedge. Put it another way, in sort of an idealized cartoon again, or with some indication of this, what we see then of what these ages would look like at the surface. Again, this is reflecting the paths that these rocks have taken into the wedge, then back up to the surface again. If we look at the distribution of ages, that's shown up here, for example, distance along the top of the wedge here, looking at the age, depending on what the closure temperature of different chronometers are, what we find is there'd be a small zone where ages are relatively young. So these A, B, C, D represent 4 different chronometers, where the closure temperature is getting higher as we go up in this list. So higher closure temperature, lower closure temperature is A. So for the highest closure temperature, there's only a small zone where the rocks have gone deep enough to expose this reset ages, or very young ages from that chronometer, whereas the lower closure temperature, is a much broader zone where these ages would be reset. And this is exactly what we see then in the Taiwan wedge. So this is looking now at 2 data sets of thermochronometric ages. On the left is apatite fission track ages, and on the right is the zircon fission track ages. Apatite, recall, is a lower closure temperature than zircon fission track. And this is reflected then in a broader zone of young ages. And that's what's sort of shaded here in this kind of pinkish, whitish shade here, is the region where the ages are less than about 1 million years, or 1 to 2 million years, where we would interpret them as being reset. Right. So this is out here, ages up to 29, 33, 22. These are the old ages. These rocks were simply not buried enough to reflect this most recent orogeny. These ages are actually retained from some older event somewhere else in the world, where these apatites had their clocks set back in say 30 million years ago. These then became sand grains that were deposited in a sedimentary rock, brought into the wedge and brought up to the surface, but never reheated enough to have their temperature reset. Back in this part of the system, 1.5, 2.0, same early history, but these rocks were carried down deep in the wedge, came up to the surface, but from depths that were high enough to reset that. On the right is the zircon fission track ages, same story, but here the reset zone is smaller than the zone for reset apatite fission track. And that's showing us again these kinematics of the wedge, which is showing that the region where the rocks have experienced temperatures high enough to reset the zircon is much smaller than the zone that's reset the apatite. If we look down to further to the south, in the furthest south region down here, for example, we see that most of the ages are unreset. These are also older ages, older than the orogeny, keeping in mind that the orogeny down here is only 1 million years old. So even 2 or 3 million years is probably older than the orogeny here. But this shows that what I was talking about earlier with the propagation of the collision, that the collision zone down here is younger, it's older in the north, and so there's been less time for erosion or exhumation of these rocks, and all of the thermochronometers are still unreset. Now, this pattern of really unreset ages in the front and reset ages in the back of the system gets more complicated if we look in detail, in particular if we look at the fold and thrust belt out on the front. So here's the foreland and the first thrusts on the western margin. And there are a number of ages shown on here. This is a little hard to read. There's quite a bit of extraneous information, but if each of these bold lines represents one sampling location with some thermochronometric ages. And there are two kinds of ages here, either apatite fission track ages, which is this FT age, or apatite helium ages, which is the AHE age here. So for example, here we have a fission track age of 31.9 and a helium age of 1.8. So what's that telling us? That's saying that the rocks in this stratigraphic unit here within this thrust sheet were not buried deeply enough to reset the fission track age, but they were probably buried deep enough to reset the helium age, which is much lower than the fission track age. If we go back across this thrust fault and look at this point here, we see an apatite helium age of 1.8, fission track age of 22. So again, the same sort of story. This area had enough erosion that it was cooling at 1.8 MA. Go back here even further, and we find an even younger apatite helium age, but now a fission track age of about 5.6. So that's saying, then go one more, and we can see again sort of that same pattern, fission track age of 3.4, fission track age of 2.6. What that's saying then is that the apatite fission track ages in this area probably were reheated. These are thrust sheets that have come from deeper. They had something else on top of them that heated them up, so that we're seeing now a cooling age of about 3.4 for the fission track and 1.3 for the helium. Those ages are then reflecting the erosion that occurred while these thrusts were being brought up to the surface. Show you one more pattern of the same sort of system across the front of the fold and thrust belt, looking in at the apatite fission track ages in blue and apatite helium ages in red. And we can again see a pattern where there are young fission track ages. So this is 1 to 4 or 5 million years. So these are all pretty much reset. But the youngest ages are found right here in the blue, the apatite fission track. The youngest ages in the helium are also found in the same area. And they get progressively older as we move away from this structure here. So what that's telling us then is that these ages are all associated with this thrust fault here. And that's saying that everything here was brought up relatively quickly along this particular thrust fault from depths large enough to reset that. In here, they may also have been reset, but earlier and exposed earlier. So these thrusts are probably a little bit older. We probably have what's called an out of sequence thrust here that's cutting across the whole stack and bringing up these rocks in the back here relatively quickly and recently compared to the ones out in this part of the system. And in fact, if we take that same profile, which you're looking at here, along here, I think this is the same or very similar along strike, and reconstruct it, what we can do is put that back together and find that in fact these were all much deeper, buried much deeper about 1 million years ago. There was something else sitting on top of that. In this case, was probably a large wedge top basin or something. And that's why these were all buried deeply, brought to the surface by erosion, and show the cooling ages that give us the timing of that. So this is a nice example where this kind of low temperature thermochronometry can be used to reconstruct the tectonic history, both in terms of the timing of motion on thrusts, but also then the timing of the erosion that was associated with those thrusts. That's just one more compilation of the same, or close up of that same before, or the current state, and then a reconstructed state for this particular section. Again, showing that there's been up to about 7 kilometers of material removed over the top of some of these in order to give those very young ages. Looking down again at the south, I pointed this out earlier, but there's a little bit closer view of the ages to the south. This is again showing that we have this transition from unexhumed rocks in the far south, where all the, particularly this is again the zircon fission track on the right. These ages are all very old, that is 44, 62, tens of millions of years. Down here, that simply is saying that we don't really know anything about the erosional history of these rocks because they have not had enough erosion to see the age. We hit a point here where suddenly that jumps from 43 to 2.3 million years. That's a rock that has been exhumed by the current mountain building, the current orogenic phase. So everything to the north here now has had enough erosion that we can see this exhumation and time this exhumational history, but in the south, we can't really say much about that. Apatite gives a similar story, except the zone goes much further south. We have very young ages here because it took less erosion to bring these up from their closure temperature. So these same rocks that have, say, a 75 million year old zircon have a 1.4 or a 0.4 million year old apatite. That's saying we've had a relatively recent shift to these high rates of erosion, and there just simply hasn't been enough erosion now to expose the reset zircons. Now, any of these ages can in fact be used to calculate an erosion rate, as I'm going to show you in a moment. But first I want to show you one more data set here that we're then going to use to calculate erosion rates, and this is detrital zircon or fission track dating. Now, by detrital, what we mean is that we're going to instead of dating a rock from outcrop, we're going to simply collect a bag of sand from a river and separate the zircons from that bag of sand and date them all. So typically, you have to date several hundred grains of zircon that come from this. The idea being that by doing so, we're averaging all of the outcrop in the upstream of this river basin. So here on the left is a map showing a number of little these black lines showing drainage basins with an outlet at the white square or diamond here. That's where a bag of sand was collected and the zircons were dated, and that's then integrated the zircon fission track ages within that catchment. The mean of that collection of zircons then is plotted on the right here as a age versus distance along strike, that is along from the southern tip of the island to the north here, and that's what's shown here. And so what we're seeing here is, again, these old ages to the south, and then a quick transition to young ages. You notice the break here between 6 and 40. So there was a quick transition here. We have sort of a group of middle ages in here, and then they quickly get very young. And this, there are 3 points for each of these that are showing the youngest population, that is the youngest zircons found in that bag of sand, versus the pooled age, which is the mean of all of those ages. And they're actually very similar for each of these samples, which is showing that in fact all of the zircons are almost the same age in many, particularly these well-behaved basins in the middle here. They're all about the same age, every zircon in that bag of sand, and it's very, very young. 1.5 or 1 million years is an extremely young zircon fission track age. But what this is showing then is again this transition from the south, where you've had less exhumation, probably at a lower rate, to the high rates in the middle, and then maybe in the north it's starting to get a little bit different again. So what kind of erosion rates do those suggest? Well, here's a transformation from using that closure depth and these ages to erosion rate. So this is erosion rate in millimeters per year, which is the same as a kilometer per million year. And what we're seeing is values from 1 up to maybe as high as 5 millimeters per year. These are very high rates. Again, this is, I mean, it all depends on what the the geothermal gradient is. There's quite a bit of uncertainty on this, but these are very high rates. That's telling us then these are coming up at 5 kilometers per million years from somewhere deep in the crust up to the surface. So this is really what we mean by active mountain building, and a good example of that active mountain building and very high erosion rates associated with that. Now, the other way that I've told you about to measure erosion rates is by using cosmogenic isotopes. So this again is a review, go back to early days of the class, explaining how 10 beryllium concentrations are used in order to calculate erosion rate. This again is based on a bag of sand method, where a bag of sand is collected at the outlet, and that tells us what the cosmogenic or the cosmic ray exposure for the entire catchment has been. And what's interesting here is to compare these. So here again is an analysis of the basin-wide erosion rates from beryllium-10, and that's what's summarized here on the right now. Number of samples along here, looking at the erosion rates along here, and these can be compared then to the fission track gauges I was just showing you. So we have an analysis of all of the drainage basins of the mountain belt along the back of the retro-wedge. Didn't analyze the pro-wedge here, just the retro-wedge. And this is the distribution then of erosion rate from both the zircon fission track and 2 different beryllium studies. And we see that they're actually remarkably consistent with relatively low erosion rates. Again, this is going from south to north. May have lost something on the axis here. This is distance, so it was tipped on the side before, but it's going from here to the north. Lower rates to the south, they start to increase, and then they're pretty much constant at some value somewhere around 3 to 4, maybe up to 5 millimeters per year for both of these data sets. Now, this is also interesting because beryllium-10 and zircon fission track are measured over different time scales. They're averaging the erosion rate over a few thousand years for the beryllium-10 to about 1 million years for the zircon fission track. And so the fact that these are consistent is telling us that the things aren't changing all that much over time, at least not over these time scales. All right. Well, that sort of segues into the next topic, which is the geomorphology. These are very high erosion rates that we found from those other dating methods. How do those translate into geomorphology? What is it that we see in the mountain belt here then that corresponds to these high rates of mountain building and high rates of erosion? Well, first of all, we see mountains. That's this is the topography. We can look at the relief, which is the local change of topography. We find quite high relief within the mountain belt as well. So topography, relief. We can look, in fact, at the way this is varying from south to north, and look at this is sort of 3 different metrics of the height or the size of the mountain belt. This again is from south to north now. What we see is that, let's just look at the bottom one. This is the mean elevation. So this is taking actually a series of transects in this direction across normal to the mountain belt, and just asking what is the mean elevation along that transect. We can also look at the total mass or the maximum elevation. They show the same pattern. What they show is at the south end of the island, there's little topography. We see an increase. And then we see something that looks like a constant value. Depends on which one of these curves you look. There's a little hump in the middle, but the max, or the max in particular, is pretty much flat. Mass above sea level, mean, they're pretty much flat. What is that telling us? Well, that's at least there is one argument that this is telling us that we're reaching some kind of a steady state. And by that, well, first of all, we have to remember what I was saying about the space for time transition here, or switch, or equivalence here. This is the old mountain belt to the north, sort of the mature in the middle, and the young to the south. We have this transition from south to north that we can think of it as both space or in terms of time. So if we think of this as not as a space axis, but as a time axis, what we're seeing is the growth of the mountain belt. We're seeing little mountains to the south, and they're increasing with time and reaching some sort of a constant value. Why constant? Well, this is this idea, if we go back to what we were talking about the Alps before and some of the other wedge ideas, that this is some kind of a mass steady state. That as the mountain belt grows, the topography is larger, the erosion rate is going to increase. When the erosion rate is finally equal to the accretionary mass flux, the size of the mountains shouldn't get any larger. And that's our steady state, where we're somewhere right between these two states of accretionary mass flux greater or less than the surface mass flux. That's our steady state. So one could argue that this transition from an increase to a flat is an example of this steady state, and the mountain belt along this region here should be in some kind of a steady state. Now, the steady state is reached in large part because of the efficiency of the climate. Remember, too, that this is the feedback that we have in these mountain building erosion systems, which is why we think we actually reach a steady state. As the mountains get larger, the erosional flux is going to get larger because both the climate changes, but also there's a larger area over which those erosional processes can operate. And we have evidence that, in fact, the climate is responding to this growth of the mountains, and that we see an orographically enhanced precipitation. This is the rainfall map for Taiwan. And remember that the high mountains are going right along this axis here too. So what we're seeing is that the high precipitation is in fact mapped directly onto the high topography. So the mountains are in fact drawing water out of the atmosphere and leading to enhanced rainfall in this area. But it's not just enhanced rainfall. It's also the nature of the type of rainfall that's important here. And this is the impact of typhoons that I hinted at earlier. This is the map on the right is maybe the most interesting. These are typhoon tracks over some 25-year period. So these are all of the typhoons that appeared and traveled across the Western Pacific. They tend to initiate in the equatorial region, and they sort of spin up and around back to the north, something like this. Taiwan is somewhere in about here. So it's really smack in the middle of this typhoon belt. And it's this rather extreme precipitation that in fact accounts for a lot of the rainfall that falls annually on Taiwan. So again, this is a precipitation map, but if I can show you a second map, all right, here's two precipitation maps. They're scaled not too differently. This is 6 meters of rain here annually. And this is the mean annual precipitation for about a 20-year period, excluding the year 2009. Why was 2009 excluded? Well, it was excluded because there was a particularly large typhoon that year. And this is that typhoon, Typhoon Morakot. And this is the precipitation for Typhoon Morakot over 5 days. And look at the scale here. The scale here, okay, here was 6 meters. This is 3 meters. But this is 3 meters, and this is the high region that around here. So the typhoon really was centered on this region. This area got order of 3 meters. In fact, it was somewhat higher than that. But this all occurred over 5 days, not 1 year. So this isn't what we call an extreme climate event or an extreme weather event. When rain hits a region that hard, that fast, over this short period of time, that induces a lot of geomorphic change. And this is what I mean by that. So here's another statistic for that. August 2009 was this big typhoon. This was 2.5 meters of rain in 48 hours that fell Taiwan somewhere in the middle here. What happens when that rain hits a mountainous region like this? Well, this is a satellite image of a portion of South Taiwan where right where Typhoon Morakot hit. This was just before the typhoon. Here's a picture just after the typhoon. Can you see the difference? Let me flash back and forth for you. Before, after. There's a lot of green missing. Before, after. A lot of green has been turned to brown. What is that brown? Well, that brown is landslides. So this is all of the hill slopes that went from green to brown there were denuded by landslides. And there were some, forget the number now, 20,000 landslides that were induced over that 5-day period of the month of the typhoon. So all the green, all the trees are being stripped off of these hill slopes and carried down into the river system along with a great deal of sediment. So when we talk about high erosion rates in Taiwan, we're measuring those with fission tracks and things like that. We're averaging over millions of years, but a lot of that erosion is happening over a matter of days or hours during one of these extreme events. So we're stripping all the hill slopes of both trees and sediment and bedrock. That's all ending up down in the rivers. This is one of those rivers about a year or two after Morakot, where all of this sediment lining the banks of this river here, back here, that all occurred during that typhoon. So there was one flood that came down, carried all of this rock. Parts of it was deposited. Of course, most of it kept on going and was deposited out to sea. What we're seeing, something like this, is just the remnants of that flood that came through that system. And these kind of events are pretty common in typhoon. This is just a typical river valley in typhoon. Very steep hill slopes. They're clearly experiencing lots of landslides, rock falls, and so on, but lots of sediment in the river too. And we're seeing a huge bed load to a little river. This is not a huge river, right? But it's got a very well-developed floodplain full of bed load. Hill slopes, very steep. To be a typical major highway crossing the island of Taiwan, very steep hill slopes. They're very prone to landslides and rock falls. Get a typhoon like that. There's also, of course, 10,000 earthquakes a year that hit Taiwan. So those are also going to induce a lot of landslides. And it ends up carrying a lot of sediment down into the rivers. Right? The longest river in Taiwan is less than 30 kilometers long, right? So we're not talking big rivers, but you look at a load like that, you're looking at something that we would see in the Rhine River or something like that, right? So it's a huge amount of sediment that's being carried out of this system. Now, the rivers are therefore very important agents of geomorphic change. And our argument that we've reached steady state means that these rivers are now powerful enough that they're able to erode and carry out all of the sediment that's being uplifted by the tectonic processes, or frontally accreted and then uplifted. If it's really at steady state and the mountains aren't getting any higher, that means that those rivers are able to compete and erode away all of that uplifted rock. But that doesn't mean that the tectonics is not occasionally more powerful than the river erosion. And we can see evidence for things like structural control on the river patterns. So for example, look at all these rivers down in southern Taiwan on the western side like this. What do we see here? We see that the rivers are often flowing parallel to the mountain belt. In particular here on the east side, it's different. Here they're flowing straight down perpendicular to the mountain belt, but on the west, they have a very strong component of parallel to the structures, if you'd like, particularly in the fold and thrust belt. And in fact, what seems to happen in a case like this is that we do develop an uplift that develops then into a fold and thrust belt, say in D or C here. So again, this is kind of an idealization of the thrust belt, in the Western foothills, with north being in this direction. The rivers get sort of trapped in the synclines between the thrust belt, and they're then uplifted and stay parallel to that until the uplift is high enough that the topographic gradient is high enough that these rivers are able to start to cut through, and they're able then to break through and begin to incise through the mountain belt. So we have sort of this transition then between, and I'm going to go back a slide, between these parallel rivers that are trapped behind structures, but then with increasing time, they get more powerful. They're able to cut through and take a more normal course across the mountain belt. And on the east side, where we don't have this same sort of thrust belt structural grain, we don't see this parallel drainage develop. All right, well, the last thing I'd like to talk about with respect to Taiwan is the Foreland Basin. Again, I think most of you have seen quite a bit with respect to the Alpine Foreland Basin, and this is an example of one that's active today. So there are sediments that are being deposited in the offshore. That's okay. Where are we here? Let's get oriented. Here's the southern tip of Taiwan. So this is the island of Taiwan through here, if you can see it. And this represents a load on the Asian plate, which is then going to be flexed downward and lead to a depression that's then full of sediment. And that's essentially what the Taiwan Straits are, between the island of Taiwan, where the mountain building, We have the old coastline out here where we have not high topography, but we've got the continental topography, and this depression between, which is the Straits of Taiwan, and why Taiwan is an island in part, is due to this flexural down warping. So the sediments that can and have been deposited are going here. We're showing at least one model of this flexure that's going from 0 up to 8 kilometers of depression. The 8 kilometers of depression, the high depression, is directly underneath the mountain belt. But then we have this sort of wedge-shaped basin here between 0 and 3 or 4 at the coastline, which is the active foreland basin. The forebulge then would be out here, and that's weakly defined, but we should be able to see that in the stratigraphy. So again, we have the topography or the bathymetry. We have this loading due to the mountain belt, and then we have this flexure downward, the maximum flexion depression here. The foreland basin would then be out here, and that's now being filled with sediments. And we can see that. We can see that in the pattern of the stratigraphy. Then here's a number of cross sections across the straits here. Which one is which? But here's 2 sections on the right, going right from the island of Taiwan on the right over to the towards the continental margin here. What you can see is an older sequence of sediments here. These brown to blue that are truncated on the side here as if by an unconformity. This would be the forebulge unconformity. Then these are the older deposits of the passive margin that are being flexed down as Taiwan grows. This is initiating somewhere really about 5 million years ago or so. So these are this is a model at the bottom. This is the observation. So over the last 5 million years, we're seeing a down flexing of the old passive margin sequence, truncation as the forebulge comes through and erodes part of that. And then we're getting deposition of these younger sediments that are mostly being shed off of the active mountain belt of Taiwan. So this would be the possibly flysch sequence in the older, but this would be the molasse type sediments, active, clastic, high energy sediments that are being transported off of the mountain belt from Taiwan. This is all forming out here then. Again, here's the island, here's the foredeep. The bulge is out here. We also have some of these other characteristics we've talked about with foreland basins, such as this wedge top depot zone. So here's the trench, the Manila Trench. This is really marking then the front of the deformation. So everything to the right of this line is being thrust today. This is the thrust belt over here. But where we go offshore, we're then getting deposition on top of this active thrust. This is then what we would call then the wedge top depot zone, right? Go back and see the definitions, but we have, if we look at, it's a little bit odd, but here's Taiwan here again, odd perspective, but here's the thrusts that are forming down in this area. Each one of these thrusts is then probably draped with sediment. The anticlines between the thrusts, if there are, or sorry, the synclines or the depressions between would be filled with sediments, forming little piggyback basins. We're getting deposition out here. Up here, we're getting into the foredeep proper, right? If there's no deformation, this is the deformation front. This would be the foredeep proper out in this area here. We also see true piggyback basins, large piggyback basins. Here again is Taiwan south. This is the southern part of the fold and thrust belt where it's exposed on land. This is a cross section across here. And in this area here, there's a large basin that's sitting in kind of a piggyback orientation here. So thrusts out this side. This is the slate belt, the metamorphic belt, which is being overthrust here. This is a largely undeformed basin that's sitting out here, some 20 or 30 kilometers across. This looks like what I was calling a negative alpha basin, or we called the molasse basin when it was activated along a thrust, or it could be just a very large piggyback basin. It's hard to say. But the scale as such is pretty big for a piggyback basin, right? But again, here we're seeing now 5 to 10 kilometers of sediment being deposited in a wedge top environment with active thrust forming outboard of that deposition. So this again is part of that wedge top depot zone. And finally, we can see the time evolution of the facies of the foreland basin out. So again, looking now at time, here's Taiwan. This is the active mountain belt. If you can see here, where's the border of the island is about here. So you can see the coastline coming through here. So these are foreland basin sediments. These this is the foreland of late Pliocene age out here. Many of these sediments now are exposed on land because they were deposited in the foredeep in front of the Pliocene orogenic wedge, which was limited to this area here. So they were deposited here, and then they've been uplifted in the younger thrust sheets, and so we can see these exposed. This would be like the subalpine molasse, for example, or the some of the molasse that's now incorporated into thrust sheets along the alpine front, and we see it up tilted, deformed, and exposed. This is the same. We can see the Pliocene or the early Pleistocene, late Pleistocene sediments. We can see both the fact that they were deposited and now are uplifted, but also see what the facies of these sediments were. And so, for example, this map is now showing the different facies from the backshore, foreshore, shore face, offshore. It's showing that these are in fact marine or shallow, shallow marine sediments that are now exposed in the frontal regions of the foreland where they've been uplifted by the ongoing deformation. So we're seeing the typical sort of sequence like we see in the Alps of deposition in a marine environment. The sediments are then carried into this accretionary wedge or orogenic wedge and uplifted in the fold and thrust belt and ultimately exposed here. Okay, that's it. Thanks much for your attention. We can, if you have questions, we can talk about them on Friday. We'll talk to you later.